In this video, we're going to learn how to find the volume of a solid of revolution using the disk and washer methods. We'll start by looking at what happens when a region in the plane is revolved around a line or an axis and how that creates a three-dimensional solid. Then, we'll go over the formulas for disks and washers, discuss how to decide whether to integrate with respect to x or y, and walk through 5 steps you can follow to set up each problem correctly. We'll finish by working through 8 examples, including regions revolved around the x-axis, y-axis, and other horizontal and vertical lines. Be sure to download the free guided notes to follow along, highlight the formulas, and work through each example with me. Let's go over the formulas that you'll need to use to find the volume of a solid of revolution using disks or washers. A solid of revolution is a solid obtained by rotating a region in the plane about an axis or a line. We'll first go over the formulas for rotating a region about the x-axis. In our first diagram, we have a region that sits on the x-axis. When we rotate this region about the x-axis, we get a solid of revolution that has circular cross-sections called disks. The volume of this solid is equal to the integral of the cross-sectional area from x is equal to a to x is equal to b. This circular cross-sectional area a is equal to pi r squared, and the radius r is equal to y, so our area is pi y squared. The volume for this solid can then be found using this formula. V is pi times the integral from a to b of y squared dx. I found that it's just easier if you write the pi in front of the integral. In our next diagram, we have a gap between our region and the x-axis. When we rotate this region about the x-axis, we get a solid of revolution that has circular cross-sections called washers. Just like with disks, the volume of this solid is equal to the integral of this cross-sectional area from x is equal to a to x is equal to b. This circular cross-sectional area a is pi times the outer radius squared, this is the outer radius, minus pi times the inner radius squared, where this is the outer radius. Each radius is equal to y, so our area is pi times y out squared minus pi times y in squared. The volume for our solid of revolution can then be found with the formula V is equal to pi of the integral from a to b, y out squared minus y in squared times dx. Whenever you use disks and washers and you're rotating about the x-axis, you're always integrating with respect to x. Let's now go over the formula for rotating a region about a line y is equal to b. The formula is written in terms of the radius and can be used for any region. In the first diagram, the line that the region is rotated about lies above the region. Since r plus y is equal to b, our radius is r is equal to b minus y. In the second diagram, the line that the region is rotated about lies below the region. Since the line lies below the x-axis, b is negative, and the radius r is equal to y minus b. It's really helpful with this formula to know that y is the distance from the x-axis to the curve, and r is the distance from the curve to the revolving line. If you remember that, you don't need to remember the formulas for r. Now we'll go over the formulas for rotating a region about the y-axis. These formulas are very similar in structure to the formulas that we just looked at for rotating a region about the x-axis, but now the integration is in terms of y instead of x. In our first diagram, we have a region that sits on the y-axis. When we rotate this region about the y-axis, we get a solid of revolution that has disk circular cross-sections. The volume of this solid is equal to the integral of this cross-sectional area from y is equal to c to y is equal to d. This cross-sectional area is pi r squared, but now our radius r is equal to x. So the area is pi x squared. The volume for the solid of revolution can then be found by the formula V is equal to pi from c to d of x squared dy. In our next diagram, we have a gap between the region and the y-axis. When we rotate this region about the y-axis, we get a solid of revolution that has washer circular cross-sections. For this type of region, the area is equal to pi r out squared minus pi r in squared, where this is the outer radius in blue, and in purple, you can see the inner radius. So the area is pi x out squared minus pi x in squared. And the formula for the volume for the solid of revolution is V is equal to pi times the integral from c to d of x out squared minus x in squared, where x is a function of y, times dy. Let's now go over our last set of formulas. These are formulas that you can use when you rotate a region about a line x is equal to a. This formula is valid for any region because the formula is written in terms of the radius. In the first diagram, the line that the region is rotated about lies to the right of the region. Since r plus x is equal to a, the radius r is equal to a minus x. In our second diagram, the line that the region is rotated about lies to the left of the region. Since this line lies to the left of the y-axis, a is negative, and the radius r is equal to x minus a. It's helpful with this formula to know that x is the distance from the y-axis to the curve, and then r is the distance from the curve to the revolving line. If you remember that, you don't need to memorize the formulas for the radius. Since finding solids of revolution is complicated, just to make things easier, I've written down 5 steps that you can follow. You're first going to graph the given curves and then find the points of intersection. In step 3, from the graph, you can determine the value for the radius, that's r, and then choose the correct volume formula. Then the last step is just to evaluate the definite integral. Let's now walk through 8 examples. I know that sounds like a lot, but each example is representative of one of each type of problem you might encounter. We're going to walk through 2 examples where we revolve a region about the x-axis. We're going to find the volume of the solid obtained by rotating the region bounded by the given curves about the x-axis. Let's look at our first example. The first thing that you want to do with these types of problems is to graph each of the curves that you're given. Just to save time, I've already done that. We have the curve y is equal to the square root of x minus 1, and then we have 3 lines. X is 2, x is 5, and y is 0. The region that we're going to be revolving is the region that's bounded by this curve and lines. That's this region right here. The radius of our solid of revolution is this radius right here, and you can see that it's equal to y. So the formula that we're going to use is the volume is equal to pi times the integral from a to b, y squared dx. And that's because our cross-sectional area is pi r squared. X is going to range from 2 to 5, and this is our y. Let's go ahead and let's put that in. Our volume is going to be pi times the integral from 2 to 5 of y, which is the square root of x minus 1 squared times dx. This is equal to pi times the integral from 2 to 5 of x minus 1 dx. This is equal to pi times the integral of x, which is x squared over 2, minus the integral of 1, which is x, and we're going to evaluate this from 2 to 5. This is equal to 25 over 2 minus 5 minus the quantity 2 squared, which is 4 divided by 2 minus 2. I always write it like this so I don't forget to take that negative and multiply it through to both terms. Let's see what this gives us. This is equal to pi. We have 25 over 2 minus 5 minus 2 plus 2, so that's just minus 5. We'll get a common denominator of 2, so this is pi times 25 minus 10 all over 2, and this gives us an answer of 15 pi over 2. The volume of our solid of revolution is then 15 pi over 2. Let's look at our second example. In this example, we have two curves. Y is equal to x squared, and then x is equal to y squared. We want to begin by finding the points where these two curves intersect, and we want to find the x value because we're revolving about the x-axis, and we're going to use x for our limits of integration. So I'm just going to write down that we're going to find the x intersection points. To do this, we're going to start with our first curve, y is equal to x squared, and then in our second curve, we're going to solve for y, and we get y is equal to the square root of x. So down here, we're going to let x squared equal the square root of x, and we need to solve this equation for x. The best way to do this is to square both sides. So this gives us x to the fourth is equal to x, and that equation we can easily solve. I'm going to subtract x from both sides, and we get x to the fourth minus x is equal to 0. We can factor this, we'll pull out an x, and we have x cubed minus 1 is equal to 0, and this gives us that x is equal to 0, and x is equal to 1. Now we can go back up to our graph, and we can see that our two intersection points are 0, 0, and 1, 1. We'll go ahead and label that. Because we have a gap between the region that we're integrating, let me go ahead and let's highlight this in green so you can see that region. We're going to have an outer radius and an inner radius. This is our outer radius, and it is equal to y, and it touches our top curve right here. So y is equal to the square root of x. And then this is our inner radius, and it touches our bottom curve. So that height is equal to y, which is x squared. The formula that we're going to use is the volume is equal to pi times the integral from a to b. We have our outer radius, which is y out squared minus our inner radius y in squared dx. This is equal to pi times the integral from 0 to 1. Our outer radius we found was root x, so we have the square root of x squared. You have to remember to square it, minus the inner radius, which was x squared, and we square that one as well. And then we have our dx. Before we integrate, let's simplify this integral. This is pi times the integral from 0 to 1. Square root of x squared is just x, and then we have minus x to the fourth dx. This is equal to pi times x squared over 2 minus x to the fifth over 5, and we're integrating from 0 to 1. It's always nice when we have 0 as a limit of integration because we don't have to do as much work. This is then pi times 1/2 minus 1/5. We'll get a common denominator of 10. So this is 5 minus 2 over 10. And we get an answer of 3 pi over 10. This tells us that the volume of our solid of revolution is equal to 3 pi over 10. We're now going to walk through two examples where we are going to revolve a region about a line y is equal to b. This is just a line that is parallel to the x-axis. We're going to find the volume of the solid obtained by rotating the region bounded by the given curves about the given line. Let's look at our first example. The first thing that you want to do is to draw each curve, and I've already done that. Here's the line y is equal to x, and here's our curve y is equal to the square root of x. The region enclosed by these two curves is this region right here. And this region is going to be revolved around the line y is equal to 1. Because the axis that this region is revolving about is parallel to the x-axis, the limit of integration is going to be in terms of x, and because there is a gap between the region and the line of rotation, we're going to have an outer radius squared minus an inner radius squared. Let's look and let's see what this radius is equal to. I'm going to draw a diagram for the outer radius, and then the inner radius will be really similar. The radius is the distance from the curve to the revolving line, so we'll label this as r. And then because our curves are y is equal to a function of x, we need to find what y is. Y is the distance from the x-axis to the curve. So let's label this as y. From this diagram, you can see that r plus y is equal to 1, and that tells us that our radius r is 1 minus y. I'm going to go ahead and highlight that because we're going to need that in a minute. If you don't want to figure out what r is each time, you can remember that there is a formula that r is equal to b minus y when the axis of rotation lies above the region. Now that we know what r is, we need to now find our two intersection points. This is going to be a and b in our formula. To do this, all we do is set the two curves equal to each other. We're going to set x equal to the square root of x. We'll square both sides, and we get x squared is equal to x, and then we'll subtract x, set that equal to 0. We can factor out an x, and this gives us that x is equal to 0 and x is equal to 1. And we're going to need this, so I'm going to go ahead and highlight that. Now we can go ahead and write down our formula. Our volume is pi times the integral from a to b, our outer radius squared minus our inner radius squared. And because our line is parallel to the x-axis, we're integrating with respect to x. Now let's find out what our equation for our outer radius is. We're integrating from 0 to 1. Our outer radius is this distance right here, and that corresponds to y is equal to x. So r is equal to 1 minus x quantity squared. And then we subtract off our inner radius. If we go back up to our diagram, this is our inner radius, and it corresponds to the curve y is equal to the square root of x. So using our formula for r, we have 1 minus the square root of x quantity squared times dx. Now all we have to do is integrate. Before we do the integration, we are going to simplify what we're integrating, and we're going to have to multiply out both terms. Just remember the formula, a minus b quantity squared is a squared minus 2ab plus b squared. This gives us 1 minus 2x plus x squared minus 1 minus 2 root x plus root x squared, which is just x. Now let's go ahead and let's pull that negative through to our last three terms. So we have 1 minus 2x plus x squared minus 1 plus 2 root x minus x. I really think it helps to break this up into two steps so that you don't forget to multiply that negative through to all three terms. Now it looks like we can simplify this before we integrate it. The ones are going to cancel. We can combine our x's, so we have minus 3x plus x squared plus 2 root x, and I'm going to write this as 2x to the 1/2, because that makes it easier to integrate. Now let's go ahead and do our integration. This is pi times minus 3 x squared divided by 2 plus x cubed divided by 3 plus 2x to the 3/2, all divided by 3/2, and we're integrating from 0 to 1. Let's see what this gives us. If we substitute in that x is 1, we have a minus 3/2 plus 1/3. 2 divided by 3/2 is 4/3, so we have a plus 4/3, and then we let x be equal to 0, and that, of course, is 0. This is equal to pi times minus 3/2 plus 5/3. Let's get a common denominator of 6. So this is a minus 9 plus 10, which leaves us with an answer of pi divided by 6. Let's now look at our second example. In this example, we have a region that we are rotating about a line, y is equal to -1, and our line lies below the region. I went ahead and graphed all 4 of these curves, and the region that we are going to be revolving is the region that is the intersection of all of these curves, and it looks like this. The first thing that we want to do is find the outer radius and the inner radius. We'll find the outer radius first, and then the inner radius will be in the same format as the outer radius. This is the outer radius. We'll mark that as r. And notice that this length is equal to y. So we can say that r minus y is equal to this distance right here, which is equal to 1. So this tells us that our radius r is equal to 1 plus y. We'll highlight that because we're going to need that. For this problem, we don't need to find our limits of integration because they're given by our two lines, x is equal to 1 and x is equal to 3. we can go ahead and write down our formula. Our volume is equal to pi times the integral from a to b, our outer radius squared minus our inner radius squared. We're rotating about a line that is parallel to the x-axis, so we have limits of integration in terms of x. Let's now put in what our limits are. We are going from 1 to 3. Our outer radius corresponds to our top curve, so this is going to be 1 plus 1 over x squared quantity squared. And then we're going to subtract off our inner radius. Our inner radius is actually a lot easier, and it corresponds to the curve y is equal to 0. So our inner radius is just 1 plus 0 quantity squared, and then we have our dx. Before we integrate, let's go ahead and simplify what we're integrating. We are going to multiply everything out. This gives us 1 plus 2 over x squared plus 1 over x to the fourth minus 1 dx. Our 1's cancel, and I'm going to rewrite this so it's going to make it easier for us to integrate it. 2 over x squared we're going to write as 2x to the minus 2, and then 1 over x to the fourth we're going to write as x to the minus 4, and then we have our dx. Now we can go ahead and integrate. This is pi times 2 times x to the minus 1 divided by minus 1 plus x to the minus 3 all divided by minus 3, and x is going to go from 1 to 3. Just to make this easier, I am going to rewrite this before we plug in our limits. This is pi times minus 2 over x minus 1 all over 3x cubed, and then x goes from 1 to 3. Let's now substitute in that x is equal to 3. This gives us a minus 2/3 minus 1 all over 3 times 3 cubed, so this is just 3 to the fourth, minus, now we're going to let x be equal to 1, so this is a minus 2 minus 1/3. Let's simplify this and see what we get. This is a minus 2/3. 3 to the fourth is 9 times 9, so that's just 81. And then we have plus 2 plus 1/3. Let's combine our 1/3 and our minus 2/3. This gives us a minus 1/3 minus 1 over 81 plus 2. It looks like we need to get a common denominator of 81. I know that sounds terrible, but it won't be as bad as it looks. 3 goes into 81 27 times, so we have a minus 27. We have a minus 1, and then 2 times 81 is 162. This gives us then an answer of 134 times pi all divided by 81. A lot of times when you do these volume problems, you don't get really nice answers. We are going to look at 2 examples where we are going to revolve a region about the y-axis, and we're going to use disks and washers. We're going to find the volume of the solid obtained by rotating the region bounded by the given curves about the y-axis. In our first example, we are given a curve, 2 lines, and a region. I went ahead and graphed these, and you can see that the region that's enclosed by all of these curves is this region right here. When we revolve this region about the y-axis, the first thing that we need to do is find the radius. that radius is this length right here, and our radius is just equal to x. Our volume is pi times the integral from c to d of r squared, which is x squared times dy. We have a dy because we're revolving about the y-axis, and the width of each circular disk is equal to dy. Our volume is then pi times the integral from c to d. C is equal to 0 and d is equal to 4. So we have 0 to 4. Our x squared is equal to y. Let me highlight that. That's right up here. So we just have y dy. This gives us pi times y squared over 2 from 0 to 4. This is pi times 16 divided by 2 minus 0, and we get an answer of 8 times pi. This example that we just did is an example where our region was lying right against the y-axis. In our second example, we have a region where there is a gap between our region and the y-axis. We have two curves. X is equal to y squared, and x is equal to 2y. The region that is enclosed between these two curves is this region right here. And we're going to revolve this region about the y-axis. Because we're revolving a region about the y-axis, we are going to integrate with respect to y, and we'll want to begin by finding our intersection points, and we want the y value for those points. We're going to find that by setting our two curves that we're given equal to each other. This gives us y squared is equal to 2y. Let's pull the 2y to the left, and we can factor out a y. And this gives us that y is equal to 0 and y is equal to 2. Let's highlight that because we'll need that in a minute. Because there is a gap between our region and our axis of rotation, we are going to have an outer radius and an inner radius. Our outer radius right here is given as x is equal to 2y, and then our inner radius right here is given as x is equal to y squared. Let's now write down our formula. Our formula is v is equal to pi times the integral from c to d, our outer radius squared, which is x out squared, minus our inner radius squared, x in squared, times dy. Let's go up here and let's label this as x out, and we'll label this one as x sub n. Now let's go ahead and put this into our integral. This is pi, the integral from 0 to 2. Our outer radius, which is the quantity 2y squared, minus our inner radius, which is y squared squared. And we have dy. Let's simplify this before we integrate it. We have the integral from 0 to 2. This is 4y squared minus y to the 4th times dy. This now, if we integrate it, is 4y cubed over 3 minus y to the 5th over 5 from 0 to 2. This gives us pi times 4/3. 2 cubed is 8, so we multiply that by 8, and then minus 2 to the 5th. That is 32, and we divide that by 5, and then we subtract off 0. To make this easier, let's pull out the 32, so we have 32 pi, and then we have 1/3 minus 1/5. we get a common denominator of 15, this is going to be 5 minus 3 over 15. So 32 times 2 is 64, and this gives us 64 pi divided by 15. And there's our volume. Often, when you do volumes of revolution, your answers don't come out super nice. We're now going to go through two examples where we revolve a region about a line x is equal to a. This is a line that is parallel to the y-axis. We're going to find the volume of the solid obtained by rotating the region bounded by the given curves about the given line. Let's look at our first example. The first thing that you want to do is to graph all the curves and the line of rotation. I already did that just to make things easier. Here's our line of rotation. And then the region that we are going to be rotating around this line is the region that is bounded by these pink curves. And that's this region right here that I'm going to mark in green. I wrote down the general formula that we can use for this type of revolution. But in our case, we are not going to have an inner radius because our region that we're revolving sits right along the axis of rotation. Let's begin by finding out what our radius is equal to. We'll go ahead and draw this. This length right here is our radius because the radius is the distance from the curve to the revolving line. And then this distance here is x because x is the distance from the y-axis to the curve. Because this distance here is equal to 1, we can write down that x plus r is equal to 1, and that tells us that r is 1 minus x. The general formula for this, when our axis is to the right of our region, is r is equal to a minus x. When I've taught this in class, I've found that some students like to memorize that formula, and some students like to just figure it out like we did. Let me go ahead and highlight what we found because we are going to need that. Now let's think about our limits of integration. Because the axis that we're rotating about is parallel to the y-axis, we are going to be integrating with respect to y. And we need to find the y value here and here. That's actually pretty easy in this picture. Our y values are going to be y is equal to 0, and then when x is 1, y squared is x, which is 1, so y is equal to 1. So we know our limits are y is 0 and y is 1. Now we're ready to go ahead and write down our formula. Our formula is our volume is pi times the integral from c to d. We don't have an inner radius, so we just have an r out squared times dy. We could have also written that as just r squared dy. This is pi times the integral from 0 to 1. Our radius, which we just found right here, is 1 minus x, quantity squared dy. Now let's go ahead and let's substitute in x. X is equal to y squared, so we have 1 minus y squared, quantity squared dy. Before we integrate, let's go ahead and multiply that quantity out. So we have 0 to 1. We have 1 minus 2y squared plus y to the 4th times dy. Now we can go ahead and integrate. This is y minus 2y cubed over 3 plus y to the 5th over 5, and we're evaluating this from 0 to 1. We'll substitute in that y is 1, and we get 1 minus 2/3 plus 1/5, and then we subtract off 0. Looks like we need to get a common denominator of 15. So this is 15 minus 10 plus 3. That's 18 minus 10, so we get an answer of 8 pi divided by 15. And that's what our volume is equal to. Let's look at our second example. In this example, our axis of rotation, the line x is equal to -1, lies to the left of our region. In this example, we have two curves. Y is equal to x squared, which I wrote as x is the square root of y. Whenever you're rotating about a line that is parallel to the y-axis, you want your equations to be in terms of x is a function of y. Our second curve is already in that format, and it's x is equal to y squared. Let's begin by finding these two intersection points. To do that, all we have to do is set our two curves equal to each other, and we want to find our intersection points in terms of y because we're integrating with respect to y. We have the square root of y is equal to y squared. Let's square both terms. So this is y is equal to y to the fourth. This gives us y to the fourth minus y is equal to 0. We can factor out a y. We get y cubed minus 1 is 0. And this gives us that y is equal to 0 and y is equal to 1. Let's highlight that because we'll need that in a minute. Now comes the hardest part. We have to find out what our outer radius is and what our inner radius is. I'm going to show you how to find the inner radius, and then the outer radius is going to be that same structure. Let's go up to our graph and let's draw the inner radius. That is this distance right here, and we'll label that as r. R is the distance from the curve to the revolving line. Let's now find x. X is the distance from the y-axis to the curve. So this is equal to x. We know that the distance between the line x is equal to -1 and the y-axis is equal to 1. This tells us that 1 plus x is equal to r. And let's highlight that because we're going to need that. Before we set up our integral, let's make sure we understand what curve corresponds to our outer radius and our inner radius. This curve right here corresponds to our inner radius because it's the curve closest to our line of rotation. And then this curve corresponds to our outer radius. Now let's write down our formula for our volume. It is pi times the integral from c to d, our outer radius squared, minus our inner radius squared, times dy. Remember, the pi r squared comes from our cross-sectional area being circular. Let's now substitute in what c and d are. They are 0 and 1. Our outer radius is going to be 1 plus x out, and then we square that, and then we subtract out 1 plus x in, and we square that out. This came from our formula for our radius right up there. And we're going to integrate with respect to y. Now we can go ahead and substitute what x is equal to. Our outer radius, let me pull that back down, is the square root of y. So we have 1 plus square root of y quantity squared. And then our inner radius is y squared. So this is 1 plus y squared quantity squared dy. Before we integrate, we want to go ahead and multiply everything out. 1 plus the square root of y quantity squared is 1 plus 2 root y plus the square root of y squared, which is y, minus 1 plus y squared, quantity squared, and that's 1 plus 2y squared plus y to the 4th times dy. Let's see if anything's going to combine or cancel. Our 1's are going to cancel. We have a 2 root y, and I'm going to write this as 2y to the 1/2, so it's easier to integrate. And then we have plus y minus 2y squared. Make sure to carry this negative through to both terms, minus y to the 4th dy. Now we can go ahead and integrate. This gives us 2y to the 3/2, all divided by 3/2, plus y squared divided by 2, minus 2y cubed divided by 3, minus y to the 5th divided by 5. And we're going to evaluate this from 0 to 1. Let's see what we get. This is pi. 2 divided by 3/2 is 4/3. So we have a 4/3. And then we have a 1/2 minus 2/3 minus 1/5. And then we subtract off 0. It's always nice when our limits of integration are 0 and 1. Let's combine our fractions that have thirds. So this is 2/3 plus 1/2 minus 1/5. Let's get a common denominator of, let's see, it's going to have to be 6 times 5, so that's going to be 30. 3 goes into 30 10 times, so this is 20. And then we have plus 15 minus 6. This is 35 minus 6, so this gives us an answer of 29 pi, all divided by 30. And that's what our volume is equal to. And that's it. You've learned how to find the volume of a solid of revolution using both the disk and washer methods. To really master this concept, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.